Hi, my name is Kate Boden, and I work with Grooms here at CU Boulder. And today I'm going to talk to you about a new DA method that we've been working on called Simplex Ensemble Transport, or SENT for short. And I need to shrink this. There we go. It's a nonlinear two-step ensemble data assimilation method, and I'm going to talk to you about it in the context of sea ice. So since the 1970s, satellites have been giving us information about Arctic ice pack, and we've seen the decrease in the Arctic ice pack for pretty much all months in virtually all regions. This image here from NOAA is showing you median extent from 1981 to 2010 in yellow, and then the minimum 2023 summer ice extent. So you can tell that there's been a big loss in Arctic ice. And we've also done projections to look at sea ice thickness distribution in the Arctic. And here we have the 1950s, where white is going to be the thick, about 5-meter thick ice. And then 2050s projection shows a pretty large decrease in sea ice thickness. And they've even done a calculation here with 54% of loss in volume of sea ice compared to the 1950s. So as we all know, data assimilation is an effective way to increase or improve our projections. And so our goal, though, is to use something more advanced than just an ENKF and to actually develop a non-Gaussian approach to assimilate sea ice concentration into models of Arctic ice thickness distribution. And we'd like to do this by respecting the constraints on the variables. So the dynamics that we're going to use IcePack, which is a single grid cell version of SICE. And in IcePack, the sum of the state variables divide the sea ice thickness into categories. So here I'm using 5 categories. I'm showing you the thickness max of each category. And so something as small as like basically 0.5 meter to about 4.5 meters. And each of our state variables that we're going to be interested in for this project are going to be the fractional coverage of grid cell by thickness category I. So that'll be Xi. This means that Xi is bounded between 0 and 1. And we have this constraint that the sum of the fractional coverage of all the different ice categories plus open water fraction, which I'm denoting here by X0, that should equal 1. So this constraint here puts us mathematically on a simplex. In one dimension, that would just be a line between, or the 0, 1. And in 2 dimensions, you can think of it as a triangle. So if we do data assimilation for sea ice concentration and we use IcePack as our model, and then the observations that I'm going to consider here, I'm going to synthetically generate them, but they're going to represent open water fraction, or similarly sea ice concentration, where I imagine that a satellite is going over my grid cell, sending down n measurements, and k of them coming back as open water. So that means my open water fraction will be k over n, or similarly sea ice concentration, 1 minus k over n. And then we could do something like an ENKF, but as we know, the ENKF assumes state variables are normally distributed, but as I described in the previous slide, our variables are bounded and constrained to the simplex. So what happens is if you just apply an ENKF, you'll get unrealistic values. Here I'm showing you an ensemble. The forecast from the dynamics is given in blue, and it lives on the simplex, which here we have we have open water fraction and 2 ice thickness categories, just thin ice and thick ice. So we're on a 2-dimensional simplex, which is the triangle. And then the ENKF will produce these values here, which are no longer on the simplex. So they're not respecting this constraint that we account for all the area in the grid cell. And of course, you could just project them back onto the simplex, and that's what's given here, the post-processed ENKF in orange. But this behavior suggests that there's something better, a better way to describe these variables. And so the approach that we took was a 2-step ensemble data assimilation approach, first introduced by Jeff Anderson in the early 2000s. And the idea here is to split the problem into 2 parts. So first, we'll do an observation space update where we're actually updating the open water fraction, the thing that we're observing. And then we'll do a state space update. And this will be our ice thickness categories. So you could do something like a regression for step 2, which maybe some of you are familiar with in the literature. But the idea here is that you're able to have more versatility in your choice of prior distributions, which allows for nonlinear, non-Gaussian relationships. So I'll talk briefly about step one, because the real work that we've been doing, or the advancement that I kind of want to entice you to learn more about, is going to be step two. But we have to still know what's happening with the update and observation space. So here, Ian worked on this and published a paper last year, where given observations, we still want to generate an analysis ensemble for open water fractions. And his approach was to use a quantile conserving ensemble filter based on kernel density estimation, so you can have this nonlinear approach. And I'm just showing you here, if you have an ensemble, so this is no assimilation, this is your forecast, and then applying the KQCEF, you get your analysis ensemble, which has collapsed around the truth. So this is already a published paper. I'm referencing it down here if you want to know more. But our work is really about step two. And I want to motivate it by talking first about scaling. So one idea is that we have this simplex constraint, right? So we know that the sum of all of the ice thickness categories in the fractional coverage plus the open water fractions should be 1. So if we update open water fraction, then we could also update all of the ice thickness categories by scaling by this update. So that's what I'm showing here in this equation. And it's a really intuitive idea, because if open water fraction goes up, then all the ice category fractions go down to preserve the fact that the sum of all the area should be 1. The limitations, though, to scaling are that you can never move off a boundary. And so I'm showing you that here, where this is kind of a toy model that I created, where you have 15 ensemble members, and I color-coded them by where they live. So we have like light blue living on this boundary, purple here, and dark blue here. And then the pink is going to be all the living in the interior of the simplex. And so if you scale, you can never make a non-zero value 0 or a 0 value non-zero. And so you have to still live on these boundaries for the other state space variables. And I'm showing you here in black how the observation has collapsed to about, let's say it's like 0.2 open water, as here the forecast is a little more widely distributed. But to kind of, I guess, entice you as to what we can do with our algorithm, is we can actually pull some of these ensemble members into the interior or even onto the boundary if that's more of a representative case of what should be happening. So I'm showing you the same prior, and here again is your observations. And so your observations, this is what would happen in step 1, but now we've actually been able to like pull these two ensemble members into the interior of the domain. So how do we do this? Well, for step 2, we take a parametric approach where we assume that the joint distribution between the state space here x0, or the observation space, excuse me, x0, and the state space x is Dirichlet. And I'm giving you the PDF here. And just to give you some intuition, if this is a new distribution for you, the value of the parameters gives you an idea of the spread in the location of the distribution. So if they're all the same value, then you're like centered on the domain. And the larger the parameter values, the tighter the distribution. It would be nice if we could just use a single Dirichlet, but we actually use a mixed Dirichlet prior. So here I'm saying this notation here is just saying the PDF is a mixture of Dirichlet distribution, where the mixture is not necessarily that we're living on one simplex and we have a whole bunch of Dirichlets on that simplex, but instead that we want to model cases where we have different dimensional simplexes. For example, here, if I take an ensemble member I, it's basically telling me that most of this variable is thin ice, open water fraction, and there's not a lot of thick ice. And so this guy would live on a different dimensional simplex than J here, where we have more ice in thicker categories. And so to account for this, this is exactly what the mixture allows us to do. So it's a mixture in the sense that we are allowing different domains for these ensemble members to live. Now the posterior Dirichlets are nice distributions. Similar to Gaussians, and people who have worked with mixed Gaussians, if you have a joint Gaussian and you condition it, you still have a Gaussian. That still applies here for Dirichlet's. So sampling from the posterior in step 2 means we are sampling from a conditional mixed Dirichlet. We still have a Dirichlet distribution, and we know that the parameters depend in a known way on the joint parameters. And we can estimate those joint parameters using the forecast ensemble and using something like maximum likelihood estimation. And we've derived all the relationships between them. It's really nice and easy to compute. So it's not so bad. You do have to update the weights by multiplying by a likelihood, but that likelihood is the marginal, and the marginal of a Dirichlet is a beta. Okay, so our algorithm, just kind of breaking it down simply here, if we're given an ensemble from the forecast and an update to the open water fraction from step 1, then we can separate ensemble members by class and determine the parameters for each Dirichlet in that class using maximum likelihood estimation, and we can determine the weights for that class. We want to generate our analysis ensemble by sampling from the conditional mixed Dirichlet. So to do this, we need kind of break it up into 2 parts. We want to determine what the posterior class should be, and we do that using optimal transport. It's kind of maybe overkill for the simple ice pack example, but for something more complicated like SICE, we can preserve spatial relationships between grid cells using this approach. And then once we know if it should change class, then we can transport individual state variables from their prior values to their posterior values using a higher dimensional inverse transform composed with a probability integral transform. Maybe hopefully that's ringing some bells for some of you, but we can talk more about that in questions if you're interested. So let's look at what happens here. This is kind of a fun GIF. So what I'm showing you in blue, that's our forecast ensemble, and in orange, that's our analysis ensemble. And this is kind of a fun demonstration of how our state is moving on the simplex throughout time. So day 200 is going to be in like the early summer, and then we're moving towards late summer. And when you start, your open water fraction is near 0, and then you're moving across the simplex to higher open water fraction. And the green star here is truth. So you could do something like an ENKF to do this as well, but you might at certain days get values that are no longer on the simplex, and you could project them back, but our algorithm does this nicely on its own. And then you could also do scaling, but for ensemble members that need to move off the boundary and into the interior, we allow for that, whereas scaling wouldn't. Okay, so I want to show you some results to actually compare what our algorithm does to current methods. So if we're going to take a forecast ensemble for 1 full year using forcing files from 2011, we'll assimilate every 5 days using synthetic data. I'll show you assimilations with the ENKF, with our 2-step DA with scent for step 2, and then 2-step DA with scaling for the second step, and then the particle filter. And I'll compare results just using a simple metric, calling it AEM, error in the absolute, on the ensemble mean. So I'm just going to compare the ensemble mean to the truth and look at the results. So a time series of this, looking at open water fraction for the summer, because this is really when things are going to be interesting for our ice pack. If you do no assimilation, which I'm calling free, you can see the ENKF still performs well, but transport or scent algorithm does better than the ENKF. We can also look at that not just in open water fraction, because that's really your observation space update or your step 1, but for step 2, when we're actually updating all of the thickness categories, ice category 1, we see again scent outperforms the ENKF. We can look at a time averaged performance. So here I'm looking at all of the ice categories on the x-axis, and the thicker categories are a little less interesting to us because there's just not a lot of ice in those thicker categories, but these thin ice and like medium thick ice are interesting. And you can see for ensemble size of 40, everyone performs pretty well for step 1, as might be anticipated because that's what you're observing. And then for ice category 1 and 2, transport or scent algorithm outperforms everybody, if you increase the ensemble size, particle filter performs a little bit better, but we do anticipate that the scent algorithm will do better in a more spatially complex model like SICE and not just IcePack. Which kind of just leads me to my conclusions. Two-step DA relaxes Gaussianity and linearity assumptions, and since the simplex ensemble transport algorithm is a novel approach to the second step for problems constrained to the simplex, it assumes a mixed Dirichlet prior, and it outperforms the ENKF when we use synthetic observations and assimilated sea ice concentration. So we'd like to continue working with this algorithm and do not just sea ice concentration, but maybe sea ice thickness. And if you're interested in this work, we're working on our publication, so you can look out for that and actually understand how scent is doing what it does. And it should be published hopefully this year. All right, I would happily take some questions.
Thanks very much, Kate, for that wonderful talk. And as the EOPAD fills up, can I ask a quick one? Are there any constraints on alphas that you used in your Dirichlet that you obey?
I mean, they're non-negative, so I'm not sure if you mean exactly, I guess that's a constraint, but also.
But is there like a limit on the sum of the alphas or something like that? Like to constrain the prior distribution, or
we don't have that in the algorithm. No. The only thing that we've like taken care of with the alphas is if you have one ensemble member in a class. I don't know if I actually did a good job describing what a class was, but it's just an ensemble member that lives on a particular dimensional simplex, then you can't use maximum likelihood estimation for that. So we just set that to be a large value so that it's basically like a delta function around the ensemble member. But that's the only like constraint that we build into finding the parameters.
Okay, thanks. There's actually a couple of questions that I see on the EOPAD. So Javier asks, did I understand well that you use a multivariate integral transform at some point in the algorithm?
Yeah, yes. Yeah, actually, okay, cool. I have some extra slides here. So maybe this is, yeah, a higher dimensional integral transform. I hope I'm getting at your question here, where, you know, normally in a probability integral transform, you pass a random variable through its own CDF to produce a uniform random variable. And if you want to generalize that to a higher dimensional case, we use like this idea of conditional chaining, where we break the problem into a whole bunch of univariate problems. And so you're like conditioning on what you know at each step. And with Dirichlet distributions, this works out really nicely because the marginal of a Dirichlet is a beta, and the way that the parameters depend in a really nice way on the joint parameters. So you know what the parameters for each one of these CDFs are, and you can pass, you know, I'm just saying S is one of the state variables through its CDF here. This is your probability integral transform, and then through an inverse transform to generate a random variable from your target distribution. And using conditional chaining for what those CDFs are, you can like generalize just the univariate PIT. I call it that because it's just kind of a mouthful to say the whole thing. I hope that answers your question.
I hope that, yeah, so Javier is happy with the answer. There's one other, like there might be more than one, but let's at least take one more question. So Risto says, thanks, Kate. Great to use more transport methods in production. Instead of open water, have you tried to use ice thickness categories in step one?
No. So we've just used open water so far, or sea ice concentration, similarly. But that would be like a next cool step for this. So we haven't assimilated sea ice thickness for step one or step two.
Excellent. So actually the next one is just, have you published this?
Yeah, so we are submitting our manuscript at the end of this month. So look out for that in QJ, and it will give much more detail into how the scent algorithm actually works that I couldn't really go into in such a short talk.
Okay, well, thanks. That's from Pirian, and with that, let's move on to let's thank Kate and move on to the next speaker.